Have you ever wondered how scientists analyze the composition of stars and galaxies? Let's embark on a cosmic journey and discover the science behind it all. At the heart of our story is a concept called spectroscopy. Spectroscopy, in its simplest form, is the study of the interaction between matter and electromagnetic radiation. In the world of astrophysics, it's a powerful tool that allows us to delve into the mysteries of the universe. Now, imagine a beam of light, born in the fiery heart of a distant star. This light, composed of various colors, embarks on an epic journey, traveling billions of miles across the vast expanse of the cosmos. Each color in this light is like a unique signature, revealing a story about the star that birthed it. As this light travels, it carries with it information about the star's composition. You see, every element in the universe, when heated, emits light at specific wavelengths or colors. These are like the fingerprints of elements, unique and distinct. The light from the stars, therefore, holds the key to understanding what they're made of. Eventually, after its long voyage, this light reaches us here on Earth. It lands on the detector of a telescope, like a message in a bottle washed up on a distant shore. Scientists then use spectroscopy to decode this message. By studying the spectrum of light, they can identify the unique signatures of elements. Essentially, they can read the star's story, written in the language of light. This journey of light, this cosmic odyssey, is a fundamental part of our understanding of the universe. It's through this journey that we can peek into the heart of a star billions of miles away and discover its secrets. So, the journey of light, a tale as old as the universe itself, is our first clue towards understanding the composition of stars and galaxies. But how does this journey of light help us decipher the secrets of the universe? Let's dive into the fascinating world of spectroscopy to find out. At its core, spectroscopy is the study of how light interacts with matter. When light encounters an object, it can be absorbed, reflected, or transmitted. In the process, light can also be split into a spectrum of colors, much like how a prism splits white light into a rainbow. This spectrum, also known as a spectral line, is unique to every element and can be thought of as its fingerprint. Imagine the spectrum as a barcode. Just as each product in a store has a unique barcode, each element has a unique spectral line. This distinctive pattern helps scientists identify what an object like a star or a galaxy is made of. Here's how it works. When a star's light reaches us, scientists use a tool called a spectroscope to split that light, creating a spectrum. This spectrum is then analyzed for distinct patterns. Each pattern corresponds to a different element present in the star. For example, if the spectrum shows a particular pattern, scientists might say, this star has hydrogen, or look, there's helium. This is possible because each element, when heated to high temperatures as in stars, emits light at specific wavelengths. These wavelengths show up as distinct lines in the spectrum, forming the unique barcode we talked about earlier. But it's not just about identifying elements. The intensity of these spectral lines can also give us a clue about the quantity of each element. Brighter lines signify a higher abundance of that element. This intricate dance of light and matter is what makes spectroscopy such a powerful tool. With it, scientists can probe the farthest corners of the universe, deciphering the composition of celestial bodies billions of light years away, all without leaving our home planet. In essence, the science of spectroscopy allows us to read the cosmic fingerprint of stars and galaxies right from here on Earth. So how do scientists go about conducting spectroscopy on celestial bodies? It's a fascinating process that starts with the capturing of light. Imagine a star, millions of light years away, emitting light in all directions. This light, carrying the secrets of the star's composition, travels through the vast expanse of space until it reaches us here on Earth. Once here, it's captured by the lens of a telescope, a device that's been used by astronomers for centuries to bring the stars a little closer to us. But capturing the light is just the beginning. The real magic happens when this captured light is split into a spectrum. This is done using a device called a spectroscope, which works much like a prism, breaking down the light into its individual colors from red to violet. This is where the term spectrum comes from, referring to this range of colors. Now, when we look at this spectrum, we see something remarkable. There are lines known as spectral lines that appear in specific places along the spectrum. These lines are kind of like a barcode, unique to each element. For instance, hydrogen has a different set of lines compared to helium or any other element. This is where the detective work begins. Scientists use sophisticated software to analyze these spectral lines. They match the lines in the spectrum of the star's light with the known spectral lines of elements. It's a bit like matching fingerprints. If the lines match, voila, we have found the presence of that element in the star. This is how we have been able to determine the chemical composition of stars, galaxies, and other celestial bodies without even leaving our own planet. It's as if the stars themselves are speaking to us, telling us about their makeup, their age, and their life story. Spectroscopy, therefore, is like a cosmic detective story, with scientists playing the role of the sleuths. But why is it important for us to know what stars and galaxies are made of, you might wonder? Well, the answer lies in the heart of spectroscopy and its astonishing impact. Spectroscopy, quite literally, is our cosmic detective. It steps into the vast expanse of space, unearthing secrets from the luminous bodies that are billions of light years away. It's through this remarkable science that we can delve into the very origins of the universe. You see, by analyzing the spectrum of distant galaxies, we can detect shifts in their light, known as redshifts. These shifts tell us that the universe is expanding, a key piece of evidence supporting the Big Bang theory, the most widely accepted theory about the birth of our universe. But the wonders of spectroscopy don't stop there. It also allows us to understand the life cycle of stars. Each star, much like a living being, goes through a birth, a lifespan, and eventually a death. Spectroscopy provides us with the tools to observe these stages. From the formation of a star in a nebula to its maturity and eventual demise, we can witness these astronomical phenomena, all thanks to the power of spectroscopy. And then there's the question that has intrigued humankind for centuries. Are we alone in the universe? Spectroscopy may hold the key to answering this. By analyzing the atmospheres of exoplanets, planets outside our solar system, we can identify the presence of certain gases like oxygen or methane. These gases could be indicative of life, providing tantalizing hints about the possibility of extraterrestrial existence. In essence, spectroscopy is our gateway to comprehending the cosmos. It breathes life into the cold, distant stars, transforming them from mere points of light into stories waiting to be told. It's our connection to the past, our lens into the present, and our projection into the future. Through spectroscopy, we can explore the universe, understand our place in it, and even contemplate the existence of life beyond Earth. What does the future hold for spectroscopy in astronomy? Well, it's a future filled with potential advancements and exciting possibilities. As we continue to explore the cosmos, we are on the brink of more powerful telescopes that can capture light from the farthest reaches of the universe. With these telescopes, we'll be able to analyze the composition of stars and galaxies that are currently beyond our reach. But it's not just about the hardware. There's also a wave of more precise software on the horizon. These sophisticated programs will allow us to interpret the data we collect with even greater accuracy. We'll be able to discern subtleties in the light spectrum that were previously undetectable, leading to new discoveries about the universe. Imagine uncovering the secrets of distant galaxies or finding evidence of elements we've yet to discover. The future of spectroscopy and astronomy is as vast and as full of possibilities as the universe itself.